During this week, this is just a program of this summer school, you will get details of how to use lasers in different fields of medicine. So I really just quickly shine a few examples to make the connection really between the physics of lasers and their applications in medicine. So monochromaticity. One reason why we need laser light to be a very well-defined wavelength, because different tissues, different constituents of the living organism absorbs light differently. So for example, in a dermatological example, you want to address the melanin, but you don't want to address oxyhemoglobin. Then you would choose a wavelength, for example, the ruby laser wavelength, that specifically targets a certain type of constituent of your body. So this is one reason why you could make use of lasers. Still the same property, the monochromaticity. Lasers, you will hear about it more during this week, can be used to measure perfusion. One way to measure perfusion is this Doppler method, when you use the frequency shift of light by the moving particles to describe the speed of the motion of the particle. And here, to be able to see the difference in frequency, you need to have a very well-defined frequency. So again, this is a reason why lasers can be used for life sciences applications. Another reason to use lasers is the very high power we can reach with the short pulses, as I explained. So either to blow up a stone in an internal cavity or to cut tissue, you would want concentrated energy, and this is also something that laser can help you with. The combination of a well-defined frequency, tunability, the low divergence, so it will shine where you want it to shine, and the short duration combines lasers a very good source for spectroscopy, because then you can target a very small volume, you can tune it to see the behavior of the tissue for different frequency light, and also you can add the temporal resolution when you look at the emitted light variation with time. It gives you extra information on what was the actual material that you shone your light onto, whether it's one type of tissue or another type of tissue. Lasers can give you a lot of information because of its special properties. Another method to describe perfusion in the body is to use the speckle method. This is also a topic that will come up during this week. And here you use the coherence property, the spatial coherence property of light, because what you do with speckle is you shine light onto your sample, and then the light that is reflected from different parts will be interfering at your detector, and this interference is only possible. You only get a very nice interference pattern if you have a very good coherence properties of your light. The precise shaping of laser beams also can be utilized in surgery. Here I have an example of the LASIK method, when you use laser to do surgery on patient's cornea, because you can shape this laser beam any way you want to, and then you can produce an arbitrary shape, arbitrary structure of the cornea. Still at eye surgery, it's very important property of laser light that you can do surgery behind a transparent medium. This is something that you couldn't do with a knife. If you need to operate on the retina, you can do it with a laser because it just propagates through the front part. You focus it down onto the retina, and then you do your surgery behind the obstacle, the eye. And the last property I want to mention is the well-controlled dosage that you can reach with lasers. So even just by absorbing the amount of laser light in the tissue and heating it up to the temperature that you want to, it's very good to use lasers because you have a very well-defined dosage. The number of pulses in your pulse train that you apply can be set reproducibly, and you can reach the different temperatures and have the different effects on the tissue that you might want to reach with your laser. So just very quickly at the end, because my time is up, I would like to come back to the ELI lasers. So now I told you that this thing which we give in hertz is the repetition rate, so it tells us how many pulses we get each second out of the laser. The second number gives us the energy per pulse. The last one gives us the duration of the pulses in the pulse train. Not the last one, the one before the last. And the last one is the wavelength of the light source that we have. And we are actually purchasing 4 different lasers for ELI, and they are state-of-the-art in their sense. One is because they are all very short durations. These are 6 femtoseconds. This highest energy one is a bit longer pulse duration, but still in a few cycle regime. So they are of different repetition rate, and because of the different repetition rate, we can reach different pulse energies, but they are all very short. And this is the main aim at ELI, to have for each experiment the suitable laser source that can drive it. And here I have the average and the peak powers of the laser systems. The very high repetition rate laser can produce terawatts, and the lowest repetition rate can produce petawatts of peak power. There are 2 missions of ELI. One is to contribute to the laser science technology, and there has been some change of paradigm. Previously, different types of lasers systems were only considered for short pulses, and we are trying now to change from a solid-state laser to fiber-based laser technology, at least at the beginning of the laser chain. Later on, it will be amplified in solid stages, solid active material stages, but we are really pushing the limits, trying new technologies. Also, how I have learned laser technology in the university lab is that you want to do an experiment, then you get into the lab in the morning, you turn on the system, you tweak everything that you can to push the laser to the limit. By midnight, you can start doing your experiments. And this is not something we would like at ELI. We are trying a different condition of operations. So we really want to offer the laser light to experiments, and we only allow for 2 hours warming or tweaking time in the morning every day. And this is something which is also unheard of. So it's not just we want high pulse energies or very short pulses, but we really want the operation mode to be different from what people working with lasers are used to. The reason why there is so much tweaking is that you really want to push your system to the limit. You want to be shorter pulse or higher energy pulse than the guy next door. So you really need to push it really, really hard. And we hope that with ELI we can do it without this much pushing, putting more technology in to start with. ELI is not just a laser source infrastructure, but we are planning secondary sources that are being driven by the lasers. And these secondary sources could be XUV or X-rays that we produce with this 800 nanometer infrared laser. it can be particles, electrons, ions can be accelerated by the very strong fields of the laser, very strong electric fields, or we also produce terahertz radiation, which is a long wavelength radiation. So this is how I could explain it. These yellow lines, they indicate the wavelengths of our primary laser systems, and then we produce some shorter wavelength radiation in the X-ray regime. Sorry about the things in Hungarian. And we also produce these terahertz radiations. This is in the microwave regime, beyond infrared, and this XUV is in the X-ray, coming close to the X-ray regime after the ultraviolet. So I started my outline with the logo. I'm coming back to the logo of the summer school. I like it very much, I must say. And I've talked about the letters in my outline, so in the outlook I'm talking about the rest. You see here this thing, which in English is called the mayfly, and this is an insect, very short-lived insect. It only lives for a few hours. And although it's called mayfly, but in Hungary they live in June, and they are concentrated on our river Tisza. Different parts of the Tisza comes at different times of June. Unfortunately, I think you have missed it because it happened a bit more than a week ago this year. But there is a really nice sculpture at the river, so I encourage everyone to look out and explore this beautiful city. Find this sculpture that gives back really the beauty of the flowering of this mayfly. And the other part of the logo that I'd like to come back to is this wave. I'm not exactly sure what was the reason to put it into the logo. Maybe Peter can reflect on that. But it could be the waves of the Tisza from which the mayfly is being born, but the stimulated emission or the laser light that I have talked in this talk. So thank you very much for your attention. Sorry about being a bit too long, but there are no talks after me, so I could take this liberty. And enjoy your time in the city of sunshine, the city of Eli, and